Hi, I'm Chris Carlson. I'm one of the senior FAEs here at Altium, and this is the second episode in our series on thermal management. Now, if you've been following along, last time we talked a little bit about heat transfer, and we developed the concept of a thermal resistance that can be used to calculate the rise above ambient temperature of our components in our design. Now, this time we're going to look at a practical application and we're going to size a heatsink for a component in our design. Now, if you missed the last episode, you can follow the link here and that will take you to the last episode so you can catch up with us. All right, now, in our example, I've got a simple little voltage regulator, an LM3940. It's a 3.3 volt regulator being sourced by 5 volts. Now, I cleverly chose a load resistor to give us a power dissipation in our regulator of 1 watt, just to make the numbers simple in our example. Now, our voltage regulator is in a TO220 package, which I've kind of drawn here. So this represents the junction of our semiconductor, and this is the back metal surface of our TO220 package. Then we have a thermal interface material and a heat sink. Now, the heat generated by our voltage regulator is basically going to flow in this direction and then be dissipated to our ambient environment. Okay? So, last time we developed a dual of an electrical model that describes our thermal model. So, let's begin there and let's model our application. You remember last time that we used a current source to represent our heat flow in watts, and then the temperature differential across each of our components is modeled by a thermal resistance. So first we have the thermal resistance, R theta, of our junction to case of our semiconductor device. Then we have next the thermal resistance, R theta, of our interface material. Then we have the R theta, thermal resistance of our heatsink. And then you'll remember that we used a voltage source to model our ambient temperature that is biasing us up to an operating point. So I'll represent my ambient temperature with a voltage source, and this it represents T ambient. So we've got our junction to case resistance, thermal resistance for our semiconductor device. Then we've got our thermal resistance for our interface material, okay? And then we have the thermal resistance of our heatsink to ambient temperature. And this is what we're going to be looking at. Now, just like in an electrical circuit, when we have current flowing through electrical resistors, when we have heat flowing through thermal resistors, we get a temperature differential. So the first temperature up here at the top is going to be our temperature of our junction of our semiconductor device. The next temperature point will be the case temperature of the back of our TO220 package. Then we have the temperature at the secondary side of our interface material, which is the heatsink temperature. And then the temperature of our ambient environment. Okay, now, manufacturers make this really easy for us. This is actually a very simple calculation to do because the component manufacturers and the heatsink manufacturers actually give us values for these thermal resistances. So, let's dig into some data sheets and see what kind of numbers we've got. I've got a data sheet here for the LM3940. And there are a couple of very useful numbers here. The first one is under the recommended operating conditions. We have our junction temperature max. So TJ max is equal to 125 degrees C. This is the maximum operating temperature we can run our junction at without failing the device. Then we have a thermal impedance, or actually a thermal resistance value for this TO220 package It's listed as R theta junction to case of 1.1. And that's these thermal resistances are always in units of degrees C per watt. It's because we have a temperature drop across the thermal resistance, and that is due to heat flow through the device. Now, the next device in our thermal stack-up is the interface. Now, I have a data sheet here for a Berrgquist sill pad. Now, this interface is very necessary in our application. If I were to mount the TO220 package directly to the heatsink, I wouldn't get a lot of thermal contact. And that's because the surfaces of these two metal objects are not uniformly flat. They actually have some roughness to them. What the thermal interface does is it provides a material to fill this gap that has a known thermal resistance, and it yields to fill in all of the little gaps along this interface on both sides. So if I didn't have that, then I would have to somehow integrate over these two unknown surfaces to figure out what the surface contact is, and that's going to be different for every application. So this brings uniformity to our application. Now, the published value for the thermal resistance of this material is 0.61 degrees C inch squared per watt. Now, this is assuming that the heat is transferring through 1 square inch of area. You remember from the last episode when we started developing our thermal resistance models, we had to consider the area over which our heat flow was being conducted. Okay, well, that's what this accounts for. So in my little TO220 package, we've all seen them, I'm going to guesstimate that the surface area of that little metal tab is about 1/4 of a square inch, okay? So what that means is that this value is going to go up by a factor of 4, which equals, 2.44 degrees C per watt. Okay, now we come to our heat sink. Now, a couple of considerations here. First of all, the published value for thermal resistance for this particular heat sink that I'll show you here momentarily is 16.2 degrees C per watt. Now, this is a nominal value that considers natural convection, no forced airflow or anything of that nature. And it's also kind of an averaged value, okay? Now, in the data sheet for your heat sinks, you'll see a little chart that looks like this, okay? Now, I know that's difficult to see, so I'm going to look at it and tell you what I see here. This is actually two graphs superimposed over the top of each other. One is for natural convection, and the other side is for forced air. Now, this gives us a thermal resistance with respect to the power being dissipated through the heatsink device. Now, if I look at the graph here and I look at my 1 watt point, it intersects right about 16.2 degrees C per watt. So this is a good number for our application. However, when you're sizing a heatsink, you do need to stare at this graph a little bit and figure out what your operating point is. Now, the other thing that is important to know here is that these numbers assume that the heat is being distributed into this entire heat sink uniformly over its surface, which is simply not the case. Our TO220 package is mounted right in the center of this surface. So our TO220 package actually looks like a point heat source. And we have to account for the heat spreading throughout the body of this thermal conductor. This is actually referred to as the spreading resistance of the heatsink. Now, nobody gives you data on this, so a good rule of thumb is to always oversize or derate your heat sinks by 30%. So if we add 1/3 to this, that's going to be in the ballpark of about 21.2 6 degrees C per watt. Okay. Now we've got almost all the information we need to determine what our junction temperature is going to be in this application. The one piece of data that's missing is our operating environment. What is our ambient temperature? Okay. Now, for this example, let's assume this is an industrial product and it must be rated at to run properly in an operating temperature of 50 degrees C. Okay. So T ambient equals 50 degrees C. Now, at this point, it's simply a matter of adding up our thermal drops. Now, keep in mind that I did, to keep the numbers clean, I did set our operating point so that we're dissipating 1 watt in our linear regulator. If we were dissipating 2 watts in our linear regulator, we would need to multiply each of these numbers by 2 to get the degrees C. Here it's degrees C per watt. Our wattage is 1 watt, so it's just the degrees C value. So keep that in mind when you're making these calculations. So what are we going to add up here? We've got our ambient temperature. We've got our heat sink rise. We have our thermal interface rise, and we have our case to junction rise. So let's see what our junction temperature is going to be in this operating condition. So we've got 50 plus 21.6 plus 2.44 plus 1.1 plus. Okay, so in this application, our operating junction temperature, TJ, is equal to 75.14 degrees C. Now, you'll notice that that's well away from our maximum junction temperature. In fact, that's we're running at roughly 60% of our absolute maximum temperature. It's a pretty good operating point. But it begs the question, what's the right operating point? Well, that's a judgment call. In some applications, you'll have a specification on your thermal derating of all of the components in your design. If you don't have that, then you kind of have to make a judgment call, keeping in mind that the reliability of an electronic product goes down with the square of the temperature. So what that means is if I double my operating temperature of all of my components on the board, then my reliability is going to go down by a factor of 4. Kind of comes down to, how long is a string? What's the right value? Again, as engineers, we need to make that judgment call. And this is a calculation that needs to be done for every component in your design. If you have any questions about this episode, please feel free to respond in the comments section below. And join us next time where we're actually going to consider mounting a D-pack directly on a board, and we're going to look at the thermal impedance through the vias and how the heat will spread from a surface of a board to the ambient temperature. I'm Chris Carlson. Thanks for your time.